Okay, so today we have got to talk about depth perception. Depth perception is our ability to see in 3D. Okay, our ability to gauge how far away something is. And we actually have two different depth perception systems. Just like with seeing color, okay, where we have two different systems that work together. Depth perception we do too. This way, if you if we lose one of them, we still have the ability to perceive depth in another way. In the 1960s, there was a study done by a woman named, who was writing just fine earlier today, a woman named Eleanor Gibson, who wanted to see. All right, she was actually at the Grand Canyon, and she was looking over the edge, and she started to wonder if babies were able to perceive depth. So what she did was she set up an experiment where she made the floor and a table all the same pattern, right? And she put a baby up on the table. Okay, she was doing this with um, kids 6 to 10 months old. And what she did was she put the baby's mother right here on the outside of the table and basically had the mother go, "Hey, baby, come here, baby." All right. And they wanted to see if the baby would stop on the edge right here or if they would continue to crawl over the side. Okay. I know you're putting babies in danger, but sometimes, you got to crack a few eggs to make an omelet. And so, um, and there was actually they had a glass panel right here. All right, so the babies were not actually crawling over to their death. All right, but what they found was that most babies by about the age of 6 months would stop on the edge right there, which was actually a lot younger than they expected. For a long time, they believed that babies were born blind. That's not true, and that they didn't have depth perception till later on. That depth perception was something that was actually developed later on. It seems like it's something that develops a lot earlier. So they found that babies could perceive depth by about the age of 6 months. Now, one of the other interesting things they found was that at about the age of 3 months, the babies would get up to the edge and they would have a reaction that showed that they understood that there was a cliff right there. Right, their heart rate would increase, their blood pressure would increase, but they would still crawl over the edge, even though they recognized that there was a drop right there. Why do you think they would still crawl over the edge if they knew that there was a drop right there? Exactly. Yeah. So it seems like this idea of depth perception is pretty innate, but we have to understand through experience that falling, right? Babies got to fall a few times before they realize that they shouldn't be doing that. So just know visual cliff experiment done to test whether babies had depth perception. So, like I said, there are two different types of depth perception. We have two different ways to perceive depth. We have a biological one and we have an environmental one. Binocular cues are is our depth perception system that relies on both of our eyes, right? It is biological, meaning it is our eyes sending signals to our brain, okay, like biological signals. This one is more bottom-up processing. Okay? So there are two different types of binocular cues that our eyes use. Retinal disparity. Retinal, meaning the retina. Disparity, meaning difference. Difference in the two images on the retina. So because our eyes are next to each other and not right on top of one another, each one of our retinas sees something slightly different, right? And then our brain puts those two images together to be able to perceive depth. You know, have you ever, like, during a 3D movie or whatever, have you ever taken off those glasses? All right. What does it look like when you take off the glasses during a 3D movie? It's blurry, and you generally see two images on top of one another, right? Okay. It's like usually a green one and a blue one. All right. And they're kind of like this. And depending how far away it is or how close it is, all right, that's creating binocular cues. So easy way that we can demonstrate this is if you get your pen or your finger or whatnot and put it like 6, 8 inches in front of your face like this, okay, and then close your left eye and look at the pen with your right eye, and then alternate. Close your right eye, look at the pen with your left eye, and just go back and forth. What do you notice happens? What happens when you go back and all right, your hand moves or your pen moves or whatever it is. When you're looking at it with your right eye, it's going to be a little bit more to the left. Actually, it's probably going to be a little bit more in the center with your right eye because most of us are right eye dominant, right? And then when you look at it with your left eye, it's going to be a little bit more to the right because we process stuff by like mostly in here. All right. Okay. That is retinal disparity. So the two eyes see something slightly different, and then our brain puts those two images together. Now, the bigger the difference between the two images, the closer the object is. All right, so the bigger the difference between the two retinal images, the closer the object. So we can pretty easily demonstrate this too. Get your pen again. All right. Well, dogs are about to bark, I think. All right. Okay, get your pen, put it up pretty close to your face, but then focus your eyes beyond the pen, like on the wall behind it. Right? Dogs, be quiet. All right. You should see Jeb. Jeb. Jeb and Cash, shut up. Okay. All right. You should see, if you focus beyond the pen, all right, you should see two pens. All right. You should have a retinal image in either eye. All right. And the difference between the two should be pretty big. Now, what I want for you to do is slowly move the pen out away from your face like this. Okay. And continue to focus beyond the pen. All right. The difference between the two should get smaller. All right. Because it's getting further away. Our two eyes are able to focus on, okay, all right, our two eyes are able to focus on things that are further away easier rather than closer. Landon, I should see Jeb. What does that mean? Okay. Oh, sorry. Yes, I was. Yeah, I went from talking to yelling at the dogs. Okay. All right. Another quick. So this is called the finger sausage illusion. All right. So what I want for you to do is hold your two index fingers up in front of your face, about a centimeter apart, and then focus your eyes beyond your fingers. And you should see, it should basically be the tips of your two fingers should look like they are overlapping in the middle. And you should see sort of a floating finger in between your two fingers. All right. And then you can put them together and it should look like sausage links, and then pull them apart and it's floating, and then you can kind of move it out and it gets smaller, move it back in, it gets bigger. All right. That's called the floating finger sausage illusion, and that's because of retinal disparity. All right. Well, yeah, like our, yes, that's what, the closer it is, that's why it says, right, the bigger the difference, because think about how our eyes are able to come inwards. Like our eyes are not able to come in like all the way in. So our two eyes see something slightly different. That's just what, and so yes, there's a gap right here. That's why you don't see your nose. Okay. All right. The other binocular cue is convergence. All right. Convergence is just basically as something gets closer. So if you hold your pen up in front of your face and then bring it up to your eyes, but continue to try to focus on it, you should actually feel strain in your eyes from doing this. Okay. That's because your eyes, as they're trying to focus, they're pulling inwards. And that muscle signal, your eyes send that signal, the muscles, to your brain saying that something is coming closer. So basically your eyes converge as things come closer. All right. Any questions about that? All right. The other way that we perceive depth, hi Jebby. Okay. The other way that we perceive depth, which is more based on our environment, is are what are called monocular cues. All right. Monocular cues are a lot of times used in art, okay, because they give us the sense of depth. They are more based on the environment, all right, and they are more so top-down processing, all right, because they are based off of what we expect to see, all right, and based off of previous experience. They are not as effective as binocular cues, but they do work. So, for instance, if you hold your two fingers up in front of your face, up in front of you like this, with one finger closer than the other one, with both eyes open, right, you should be able to pretty easily tell which one is closer, right? But when you close one of your eyes with them at a different distance, it's harder to tell which one is closer. Okay. All right. So if you have them both open, you can pretty easily tell, but close one eye, it's harder to tell. All right. That's going back and forth between binocular and monocular. These are pretty easy. So I'm going to go through them pretty quick. We have 15 minutes, so that's actually perfect. So, like we said, this is all based on what we expect. Relative size. when when two things, when two objects, when we perceive two objects of being similar sizes, the one that is smaller in our retinal image is the one that we perceive as being further away. So in this right here, we have all these different balls. Okay. This ball is smaller than this ball, right? And so that gives us the sense that that ball is further away than this one is. Okay. Size is relative to distance, as long as the two things are perceived as being similar sizes. All right. Or then, for instance, here's me right here in the foreground. Okay. And then it's harder to see, right? But there's another person right there. All right. Because I am bigger, all right, because we perceive that, we're both basically about the same size, all right, because I'm bigger, I'm perceived as being closer than this guy right down here. Okay. Relative height. Relative height is also, height is relative to distance. In our visual field is meaning what we see. Things that are lower in our visual field are perceived as being closer. Things that are higher in our visual field are perceived as being further away. All right, so even though these two trees are the same size, this one's higher in our visual field, and so we perceive it as being further away from us. Okay, or like here, you see me right here, and then these mountains up at the top. All right, these mountains are further away because they are higher up in our visual field. All right, are there any questions about those two? All right, interposition. Interposition is when we have an object that is blocking another object, we perceive the object that is blocking as being closer to us than the object that is being blocked. So the circle is closer than the square is closer than the triangle. Right? Or here, we have this cow that was trying to get into this person's shop. The cow is blocking part of the person. All right, therefore, we see the cow as being closer to us than this guy right here. All right. Linear perspective is when we have two parallel lines, all right, such as on a railroad track or the sides of the road or whatever. As they go off into the distance, we perceive them as converging. All right, we perceive those lines as coming in closer to one another, when in fact they don't. Okay, this is also due to relative size. Size is relative to distance. The size of the road, it looks like it gets smaller, right, the further away it gets, but the two parallel lines seem like they converge. All right, same thing here. All right, you can look, the sides of the road look like they come together right there. All right. And then the last two, light and shadow. All right, light and shadow basically says when something is illuminated, we perceive it as being closer than something that's in shadow. Okay, the brighter an object is, the closer it is. So in this picture right here, all right, the parts of the circle that are the lighter colors, are we perceive as being closer. It gives us the sense of depth, and we perceive that as being closer to us than the darker parts. All right. Or same thing here, the part of this that's lighter down at the bottom, we perceive as being closer than the part that's not reflecting as much light. All right. And then relative motion. Relative motion is when we are moving. If you're moving, say you're in a car, and you fixate on a certain point, the things that are in front of that certain point are going to move the opposite way that you're moving. So if you're moving forwards, it's going to look like they're moving backwards. And then everything else beyond the point that you're fixating on is going to move with you. Right? And the further away something is, the faster it appears to move. This is also why, like, has anybody in here ever been on a train and you're sitting on a train and there's a train right next to you, and all of a sudden the train right next to you starts moving one way, and you get the sensation that you're moving the opposite way? Okay, you ever had that before? It happens in cars too. All right, that's also relative. That's relative motion, or it's also called motion parallax. All right. Are there any questions about those? You really just need to be able to recognize a definition of them, and maybe an example, maybe like a picture. All right, so here are some examples. Like we said, we use these a lot in art. So like this street art, giving the sense of depth, like this one right here. Like this guy is not actually there; it's a painting, right? But gives a sense of depth. All right, same thing here, using linear perspective, using relative height, relative size. Okay. Same thing here, light and shadow up here, saying that this is closer to us. Okay. All right. And then here, I don't know if you've ever seen in Europe, a lot, they do this more in Europe, but they'll have like, they'll make a 3D picture of like children playing on a street, and from a certain angle, it'll look like, when somebody's driving, it'll look like there are kids playing on the street, which makes people slow down. Right. And same thing here, like that basketball is not actually there. All right. It's just using light and shadow to give the perception of depth. All right. Are there any questions there? Stuff is pretty easy, I think. All right, last thing, before I let you go to do asynchronous. Phi phenomenon. Phi phenomenon is our brain's tendency to perceive when we see blinking lights, like in like when like in like Christmas, when people like put lights on their house, and maybe the lights are like synced up to music or whatnot, or they do like different patterns or whatever. We actually see that as a continuous thing of light moving through those lights, when in fact it's actually just one light lighting up after another. So with this lilac chaser, you see this as like an entity that's moving from circle to circle, when in fact it's just, if this was real lights, it would just be one light lighting up and then turning off, and then the next light lighting up and turning off. It's not that there is actual light traveling from one bulb to another. It's also called beta movement. All right. So we're going to finish the rest of this PowerPoint next class. Just a little bit left, perceptual constancies. So what you're going to do for asynchronous. And like I said, not going to do that, not going to do stuff like this a whole lot. All right, but for stuff that's pretty easy, just kind of like memorizing, all right, I might. Okay, so you're going to go to this Crash Course Psychology number 6, homunculus. It should say 6 other senses. All right, we have 7 senses. We've covered 1 with vision. All right, you're gonna. Okay, you're gonna make a copy of the questions, and then it's just a 10-minute long crash course video. Okay, you're going to answer the questions as you go along, and then you are going to submit those questions for a grade. All right. Okay. You can either copy and paste the questions in your answers, you can submit the Google Doc URL, or you can download it as a Word document and upload a file. Okay. So I don't like whenever if you want to do it right now, you can. If you want to wait and do it, you can, but it's just got to be in by Wednesday, all right? Because this is something that's going to go on to quarter 1, all right? I wanted to make sure to get you all as much points as possible for quarter 1, all right? So, anybody got any questions? Let's see.